This one.
So yeah, thank you everyone for joining, and it's been always a pleasure to see you guys here and talking about mathematics. Today, our guest, which will be delivering the lecture, is Muhammad Awais. Awais did his bachelor in mathematics from University of Punjab, and then he followed by a one-year mathematics course at the IMM Lahore. After which he got the opportunity to participate in the postgraduate diploma program in mathematics at ICTP, and currently he's doing his master in a joint master program of SISSA in University of Trieste. Today he will be talking about what loop can tell us and understanding fundamental group. So over to you, Awais.
Thank you very much, Rizwan and Wajid bhai. So before sharing the screen, I want to say something in video. So I will come to screen after some time. So wait. Okay. I hope anybody can see my video. So first of all, this lecture is going to be very informal and very basic. So the guys who are already expert, so maybe it will not helpful to them, but for beginner it will be. I hope it would be a bit helpful. So the very fundamental question in topology is that, like, how we can differentiate different topological space, like how we can say these two topological space are same or not. So the mostly mathematicians are working to find out some invariant. So if two spaces are differing by these invariants, so we can say like these two topological spaces are not same. So fundamental group is one of these invariant, and I will show some object. These object I have in my room, so I will use them. So let's say you have okay, this is a space, like it's a topological space. Okay, assume like it's hollow from inside. Okay, so one can see like it's up to topology is a sphere. And also I have another space you can see here. Okay, and there is a hole inside it. So the question is like, are they same or not? But how I can make differentiate among them? So there, so it's not like a easy question, like how I can, okay, maybe intuitively I can say like they should not be same, like I can't continuously deform this space to make that space. But why? Like we have to be formal in mathematics. So then idea goes back to Poincare. He gave the idea of fundamental group. So let's see. Okay, let's say you have this space, okay, and I have a loop on that space. You can see like I have a wire which is actually lying in that space, okay. Now if I continuously move that wire, I am moving continuously, you can see, and remaining on my space. And also I'm using, okay, I'm not like, my wire is not such flexible, so but just imagine it's such flexible, like it is like all the journey it is traveling on my space. Okay, so you can see like after moving it, I am able to shrink, contract this loop. Okay, but if I come back to that space, okay, and if I have a loop here, and you see like when I'm trying to contract it, I'm doing, but now after that I'm not able to, because after that when I'm not able to contract it, because it will no more on my space, because this part it's a gap, like it's not the part of my space. So it means like the loop, like this loop, I am not able to contract it on that space, but at same time on that space I was able to do so. So it means like if I am able to give a formal theory of loops, and I have hope to differentiate among these spaces, like this space and this space, they both are not same, because at that space, I was able to contract every loop, but at that space, I am not able to do so. I give you example like the loop, which I am not able to, because either I can use um, this way or either I can use this way. Okay. But in both direction, there is a gap. So continuously, I can't contract a loop on that space, but and that space I can do. So it means like if I'm able to, if one is able to make a formal theory of loops, so it we will have something positive at the end. So the lecture of today is going to discuss this theory, like very basic, and I will be very informal because I just want to give ideas to student. I don't want to make them bore by proving stuff and by like giving the formalities and details. If one will be interesting, so he can read. There are many references and resources. So let's come to our presentation. Okay. So I hope anybody can see the screen. Are you able to see my screen?
Yes, yes.
Okay. So the so, so to make the theory formal, to have some to go on this way, like which I mentioned, like with the intuition which I gave earlier. First, we have to define what is path. So let X be a topological space. A continuous map P from interval to X is called path, and it's very easy to see. Like one can see the picture. Like this is path. Okay. No, as you see, like in my when I was giving the intuition, like I have a loop which is a path. Okay, loop is a path. No, I was kind of traveling my loop on my space. So I have to give the notion like how I can make this thing formal, like how I can give these formalities, mathematical formalities to this intuition, like how I can travel the loop on my space. To deal with that idea is called homotopy. So homotopy between path. Okay, let P and Q be a two paths in topological space X. We say P is homotopically equivalent to Q if it means like I can transform P continuously to Q if there exists a map H from interval cross interval to X, and this sorry uh, this part, like this part of this coordinate, this parameterization represent the time, and this parameterization represent the path. So it means like when I at time 0 I should have my original path, and at time 1 I should have my final path, and this is the homotopy, like this is the all journey which I travel on my space. So like this was my beginning path. Then I define homotopy. Along that homotopy, I'm moving my path continuously, okay, with time. And finally, I have this final path. And I want to show this thing, like I have some, I made some graph just to give like what is the idea. You can see my Chrome.
Yes. Yeah.
Okay. So you see, like I have two path here. Like my space is R2, and this is a red path, and there is another a green path. Okay. Now I define a homotopy here. One can see here, this is a homotopy which use variable A and T. Okay. Here A is representing time and T is representing the like the parameterization of paths. So when I move continuously A from 0 to 1, so you can see like I am moving my path. Okay, you can see continuously I'm moving my path from one path to another path. Yes, this is the way. Okay, so this is the meaning of homotopy. Okay, so these are the examples. Like let's say you have a So one can see many examples in some references. Okay, now we define homotopy relative to endpoint. So is exactly like the same as homotopy, but now throughout the journey, I don't want to leave my endpoint. Okay, so let I have two paths, P and Q, such that starting point of P is exactly the starting point of Q, and end point of P is exactly the end point of Q. You can see in picture, I have a path P whose starting point and is exactly the starting point of Q, and end point is exactly this end point of Q. Okay. Now I'm interested in the homotopy, which throughout the journey I'm not going to leave my endpoints. Okay. So how mathematically I write it? So a homotopy relative to endpoints, if it satisfies extra condition, that is, what is the extra condition? Like for all time, the starting point of my path with respect to that time, it exactly should be equal to uh, starting point of P, which is a starting point of Q by assumption. And similarly, this assumption should hold for endpoint. And one can see again this thing in graph. I have two paths. Let's say this is a green and blue, and their starting and end points are same. So now I define a homotopy, which one can see here. So now when I move uh, with respect to time, so you can see like I'm moving one path to another path, but throughout my journey, I am not leaving the endpoint. So this kind of homotopy is called homotopy relative to endpoints. Okay. Okay. So good. So now let's assume we have two paths. One is path P and another path is Q. But now the assumption which we are having, the end point of path P is the starting point of path Q. So one can see here, like this black path is path P, and this red path is path Q, but the end point of path P is exactly the starting point of path Q. Okay. So in this way, I can define a new path, which called the product of these two paths is denoted as P dot Q as follows. Like this is the mathematical formula is given here. But the idea is that now one can imagine, like when I define the path P, so I gave some parameterization. So it means someone is traveling along that way with some speed. Okay. And similarly for path Q. Now what I can do, I can travel this path P if I double my speed. So in this way, I will be able to travel this path in half of the time. So I will define new path. So I will double my speed here, and also I will double my speed here. So this new path will be, remember the definition of path is that a map from 0, 1 to space X. Okay. So I should be able to define a map P dot Q from 0, 1 to my space. So in this way, what I will do, in half of the time, I will travel this P, what I will do, I will double my speed to do so. And similarly, in half of the time, I will travel Q. So in this way, I will be able to define this new path P dot Q, which is written here. And one can easily prove using pasting lemma, this is a continuous mapping. So I will be able to have a new map, which will be a path whose starting point will be exactly the starting point of P, and end point will be the end point of Q. Okay. Now let's come to our, like, as we see, like in our previous example, we are interested in path whose starting and end points are same. Like I am interested in, like, what I will do with path. I need something. I want loops. Okay. So the definition of loops is here, like the path whose starting and end points are same, they call loop. So one can see the picture here, like this is a, like, okay, by definition, this is a path, but this kind of path we treat specially, and we call them, they are sorry, they are loops. Okay, now, so let X be a topological space, and fix some point x naught in your topological space, a point which you like. Then we define this space of loops based at x naught, and this space is given as follows. Like we consider all the path which are actually loop, which one can see here this condition, like all the loops whose starting and end point is the x naught. So this space called loop space based at x naught, and one can see picture like I have a x naught and I drew some loops. So like all possible loops in my space, if I have fixed some x naught, so this space called loop space based at x naught. Good. Now let's come to our main hero of our presentation, is fundamental group. No, so it's defined as like space of loops relative, like if I quotient with this relation, which is relation homotopy homotopy relative to endpoints. So equivalence classes of all the loops with respect to that relation is called fundamental group. Okay, so if I am saying it's a fundamental group, so it means like for the moment, it has nothing to do with group, but it's some kind of space. But why, like if you see like in with respect to like that relation, if you can see my video, I don't know, this loop, and if I continuously shrink and this loop, they both are same, because I can at this loop I can continuously move to that loop, so it means they are equivalent to each other. So in this relation, these both loops are same, so that's why we are interested in this relation. Like we want to like the loop which I can continuously shrink or transform or move to other loops, I want to treat them same, so that's why this relation is important. So this is the definition of fundamental group. Okay, and this, for the moment, it depends on the base point x naught which we choose. Okay, so the theorem is that this, okay, we denote fundamental group as pi 1 of x, and it's based at x naught. So the theorem is that it is a group under product of loops. So the product which we defined earlier, so one can prove like it satisfies the axiom of group. So generally it's non-commutative group, but it's a group. And the proof is available in this presentation. If someone is interesting, I can share to him, but I'm not going to give the detail. Okay, so let's see some examples. So but the problem is that I told in very early, like I'm not going to I'm not going to be very formal. So, and also with that machinery and with these definitions and with these discussion, it's not possible to prove these examples, but one can actually visualize it why it should be true. So first of all, the fundamental group of R2 with respect to origin is trivial, and this is actually we proved earlier, like not we proved, but one can prove very easily, like whatever loop you have, and as R2 is convex, and using convexity one can easily prove, like we can shrink this loop. So as we are not proving other stuff, so I think to not prove it, just to see this thing intuitively. So just wait a second. Okay. So let's see, like this is your plane. So So, but okay, this is your origin. Okay, so whatever loop you have, okay, so you can see like there is no restriction, there is no obstruction to shrink it. So it makes sense to say like fundamental group of plane with respect to origin should be like whatever point you take, okay, should be trivial, okay. But at the same time, if one asks me to compute the fundamental group of plane minus 1 point, so then one can see intuitively it should not be trivial. So let's say this is your plane, okay. Now I'm removing that 1 point, okay. I remove 1 point, okay. Okay, so yeah, I hope you are able to see my video.
Yes, we can see it.
Okay, so this is a plane, okay, and let's say this is your base point, like 0 0, like origin. I am making dot here, okay. So now if one has loop, I will try this. So if one has this loop, so it is easy to one can see like one can contract it, shrink it, as the example of R2. But in this loop, we can't shrink it. Like whatever try you will do, when you will try to shrink it, so there is a gap. So you can't jump it continuously. So it means this loop is something which you can't shrink. It's not trivial. So this says like fundamental group of R2 minus 1 point should be something non-trivial. Okay. And one can see like why it should be Z. So one can relate, like one can make a isomorphism in this way. Like if I have this loop, let's say this is my direction. So it is winding 1 time, but I can have loop in this way, which wind 2 times. Okay. And one can see like this 2 time winding is not, one cannot transform this 2 time winding to 1 time winding. Okay. So it means like this 1 time winding and 2 time winding, they are different. And similarly, one can define in opposite direction. So in this way, so this is the idea, like one can say like fundamental group of plane minus 1 point is that, okay. So like it is the isomorphism is given by these windings, like how I'm winding, and depending on its direction. If it's positively winding, so it means this positive integer, and similarly with negative. And with zero winding, like I'm not going towards this removed point, like my loop is traveling here, so it means this loop can be shrinked, so it is a trivial element. Okay. So similarly, the fundamental group of sphere based at, let's say, north pole, it should be trivial. And this is the like the very early example which I gave. So you can see like the whatever loop you have, either you can shrink from that side, or either you can shrink from that side. Okay. But this is very intuitive. Still, like to prove them, we need a slightly higher machinery. Without, like, it's not easy to prove just by this definition. Even the fundamental group of R2 minus 1 point are sphere. So we need something to do with them, but at least the idea is clear. And the main purpose of this presentation to just give the idea to beginner. Okay. And one can see here, like if I have R2 minus this point, which is which I represented as like a cross mark. So if this loop, one can easily contract because there is a space among it, so one can contract it. But this loop, if you will try to contract it, so this gap will not allow you to contract it. Okay. And similarly, likewise, the fundamental group of sphere is trivial. So whatever loop you have, you can travel, like you can keep traveling it, and you can shrink it at the end. Okay. So the question is that, does the fundamental group depend on the base point? Like if you remember in the very beginning, we said choose a base point and define a fundamental group with respect to that base point. And the second question is that, is the fundamental group topologically invariant. Like this is the thing which we wanted to do in very beginning. I said like the idea is to give us some new invariant to topological space. So we gave something. So the question is it the thing which we wanted to do? But the answer is to both question is yes. The first question is depending on your situation of your space. So if this space is path connected, let X be a path connected topological space, then whatever base point you choose, your fundamental group will be isomorphic. But it's not true if your space is not path connected. For example, if I consider this space like the disjoint union of these two spaces, okay, and if I choose base point here, the fundamental group will be trivial. But if I choose base point here, fundamental group will not trivial. Okay, so it depends on the base point. But if the space is path connected, so it does not depend on the base point. So it means like we can work with space which is path connected, and we can remove this extra x naught, and we can say pi1 of x. Okay, so it is whatever base point you choose, it is a fundamental group associated to your topological space. And the proof is very easy. Let's go. Okay.
Awais, before
Yes.
you go to next slide, I think Shah wanted to add something or ask something. So
Okay.
I'm unmuting him.
Okay.
Shah, you can speak now.
Oh, I think it's late. Maybe it was a previous slide when you were talking about the groups for R2 and S2 minus a point.
This?
You can here. So, I mean, for the S2 minus a point, you can remove the north pole and then the stereographic projection, you just get R2.
No, like this is not S2 minus a point. It's a S2 and this is a base point.
Right. Yeah, okay. It's still, I mean, it's just a sphere, so you can draw a picture.
Yes, so that's like I drew a picture here. So the idea is exactly as you said, like we can remove North Pole, and this is like the any loop can be seen as in R2. But yes, this is also a good idea to actually, but there are some problems like this space filling curves and so on.
If you give me a loop on this the surface of the sphere, you can always push it a little bit through homotopy away from the north pole, so you then get a loop in R2 to contract it.
Yes, we can get loop in R2, but yes, you are right. But the problem is that like where the theory which we are developing, our homotopy have to respect our base point. So like pushing it a little bit from base point and then defining homotopy, then at the end we have to come back to our base point.
I meant is what I meant is like you choose a base point away from the north pole and then push it away from the north pole. So then you get a loop in R2.
Okay. Yeah, that could be another idea to prove. Yes. Should I start?
Yeah, thank you, Awais. Please.
Okay. So if our space is path connected, so a fundamental group does not depend on the base point. So whatever base point you choose, so you will have same isomorphic group at the end. So we can say like we can define fundamental group like from now we will, okay, I didn't write it, but from now, if our space is path connected, so instead of writing pi1 of x comma x naught, we will write pi1 of x, okay? Because it doesn't depend on base point. At the end, we will have isomorphic group. Okay, so let's, okay, so the second question, which is the most important question, like is this invariant, this association which we are given to a topological space, does it respect the topology? Like if our two topological spaces are same, should I have the groups same? So that's an important question. So the answer of this question is given here, yes. So we should be happy. So let phi be a continuous map, okay, x to y. So we define phi star. We call it push forward. So we define phi star from the fundamental group of x based at x naught to pi 1, like fundamental group of y based at phi of x naught. Okay, and how we define this map is given in this way: phi star of a loop p is equal to phi composed with p. And one can see easily, like if I have a loop based at x naught, this phi composed with p will be a loop based at phi of x naught. Okay, so if I define the map in this way, like if I consider p, okay, actually there is a bracket here, like I'm considering equivalence classes. So there are some mental exercises to prove this push forward is well defined. Okay, and it's also, one has to prove it's a group homomorphism, which is not very much difficult. Okay, but the important property is that if you consider the identity from x to x, then you consider its push forward identity star, it exactly give you the identity at group. So that's the important thing. Like when you have identity, when you take push forward, it gives you identity, and it is obvious thing to see from here directly. Okay, because when phi is identity, phi identity composed p will be p. So identity star of p will be p. So it makes sense. The second property is that when you have a map from x to y, then y to z, and when you define this psi composed phi and you take its push forward, you get psi push forward composed with phi push forward. Okay, and it is also easy to see with some effort. Okay, so now from with these two property, one can see like this fundamental group is a topological invariant. So how one can see, so let x and y homeomorphic space. So it means I have a continuous map x to y, like a bijective continuous map whose inverse is also continuous. So let's say f is a map and its inverse is g. So when you consider f composed g, you get identity by definition of homomorphism, and g composed f, you get identity by the definition of homomorphism. Okay, so this by second property, you will have f star composed g star equal to fg star, but fg is identity, as one can see here. So you get the identity of y, then push forward. But with first property, you get identity at the level of fundamental group. And similarly with the G star composed F star. So it means F star and G star are inverse to each other at the level of fundamental group. So it means like if your spaces are homomorphic, the fundamental group should be homomorphic. So if one is not able to see these details here, in such like in for this fast presentation maybe, so one can easily see it and sit and just write them, and one can convince himself. But the main idea is to understand like when your spaces are homomorphic to each other, your fundamental group should be isomorphic. And also this push forward is important. Whenever you have a continuous map from x to y, you can define a homomorphism of group with respect to this phi as phi star from fundamental group of x to fundamental group of y. Good. Okay. So before going to applications, I wanted to assume something. Like I know I have not proven, but I can assume at least. So I gave the idea fundamental group of R2 minus 1 point. No, I am not using base point because I know R2 minus 1 point is path connected, so I can drop the base point because they all are isomorphic. So I gave the idea like R2 minus base minus some point, let's say origin is Z. Okay, and one can also convince himself like fundamental group of S1 is Z. And the idea is exactly similar. Like when you have a, if you remember, like when we prove like the fundamental group of a plane minus 1 point is Z, but this minus 1 point, like you can make this like this gap bigger and bigger. Maybe you can have analysis and keep doing. You can have a circle, and okay, let's say when you have a circle, so if this is your circle, okay, so when you have this loop, okay, let's say starting from here and it comes to this end point, you can't shrink it like this. Shrinking, like you have to use this gap, which is not possible. So it means this is a non-trivial loop, okay. So similarly, you can wind 2 times, so and so on, and similarly with negative direction. So fundamental group of S1 is Z. I told you like this presentation will be very informal, because if I need maybe 2 to 3 lectures to give the proof of all of these fundamental groups and some details. Okay. Fundamental group of D2 is exactly similar like R2. So it's a convex, so every loop you can shrink, so it is trivial, okay. And the last thing, fundamental group of R3 minus 1 point. So let's say like you are in 3D space, here I'm sitting, and maybe this point is removed, okay. So okay, I'm in space without that point, okay. So let's say I have a loop here, okay. So let's say whatever loop you have a lot of space to contract it. Like let's say this point is removed, you have loop here, you can contract remaining here. You have loop here, so you can continuously move because there is a lot of space around that point. Come here and then contract it, okay. So fundamental group of space like R3 minus 1 point is trivial. Okay, the first application, like it's very basic application, is that R2 is not homomorphic to R3. I don't think so. If one has other way to prove this thing, if one has, I don't know. I will happily accept it, but this problem looks very like easy, like R2 something like 2-dimensional thing and R3 something 3-dimensional thing is not possible. They are homomorphic to each other. But it's not very obvious to prove them. Like how you can prove it? They are very innocent statement, but using this fundamental group technique, one can prove in these 2 lines. One can see they are not 2 lines actually. There are a lot of lines behind. We didn't prove R2 minus the fundamental group of R2 minus a point and also R3 minus a point, but after proving them it's just 2 lines. So let's say, okay, assume R2 and R3 are homomorphic to each other. So let F is a homomorphism between R2 and R3. Okay, so when 2 spaces are homomorphic to each other, so if you remove a 1 point here and image of this point there, so they should be homomorphic to each other because same map, the restriction of same map will work, okay? So this implies R2 minus a point is homomorphic to R3 minus a point, but they both have different fundamental group. As we see very informally, like the fundamental group of R2 minus point is Z, and fundamental group of R3 minus 1 point is trivial. So they are not homomorphic. So that's a contradiction. So it means R2 minus R2 is not homomorphic to R3. So it's good. Okay. Let's see some. This is another application. It's very important theorem, like fixed point theorem. Just read the statement is such a fancy statement. Like if you have a continuous map from D2 to D2, so D2 is a disk, like a disk like in R2. It's a closed disk. Like all the point whose distance from origin is less or equal to 1. So if you have a continuous map from D2 to D2, so then there exists a point such that f of x is equal to x. It's a very fancy statement, like whatever continuous map you have from disk to disk, it should always have some fixed point. And it is, you have seen this thing in one-dimensional case. So whatever continuous map you have from interval to interval, so there should be a fixed point. So you, like everyone in bachelor, I hope, is aware of this statement. Using maybe intermediate theorem, one can prove easily. But at disk, like at dimension 2, is actually very non-trivial statement. But using the fundamental group, one can prove. So let's see. We want to prove we have a continuous map from D2 to D2. And we want to prove like there exists a point x such that f of x is equal to x. So like it's like, let's say you have a plate and there is a sand inside it, okay, and you shake the sand, but after shaking it, there will be a point of sand which will be at his position where it was in the starting point. Like one can see the this analogy, like if your shaking is continuous. I hope it is continuous. Anyway, okay, let's prove it. So assume contrary is not true. So what is the contrapositive of our statement? Like for all x in our disk, f of x is different from x. Okay, so one can see a picture. So this is, let's sorry. Okay, so let's say this is your x and this is your f of x. Okay, and for all x it is different. Okay, so now define a map from D2 to S1 by the way shown in the figure below. And how we are defining a map from D2 to S1 and how we are defining, choose a point. Let's say this is your point, you choose a x. Okay, then there is a corresponding f of x with respect to that point, and it's different by assumption. So now we can define, we can make a ray from f of x to x, and to and the point where it will intersect, we will say this is the image of R. And it is this map is well defined due to that fact, f of x is not equal to x. If you assume f of x is equal to x, let's say this is your point x, and f of x is also lying on that point, then there are infinitely many possible rays. So it's not a well-defined map in this way. It is well-defined because we have this assumption like x and f of x are different, and from two different points, there is a unique line passing through these 2 points. But if the point is same, like from one point, there could be infinitely many actually. So in this way, your map could not be well defined. But with our assumption, this map is well defined, and one can convince himself this is a continuous map, because a small change in x gives you small change in image, and so on. Okay, so we have a continuous map from D2 to S1. Good. Okay, but also if you see, but this map, if you restrict R on S1, you get identity. How? So let's say this is your x on the boundary, and whatever f of x is, your ray will come to x finally. So when you restrict your map on boundary like S1, you get identity map. So this is a key observation. Okay, so with that we have, if you take an equation from S1 to D2, then you take this map R, which we define, to S1, you get identity, because you take some point here, it goes to exactly that point, But as I mentioned earlier, the restriction of this map on the S1 on boundary is identity, so it will go to exactly same point. So this is identity map from S1 to S1. Okay. So we have R composed with identity is R composed with inclusion is identity map. So when we take the, so we can take the push forward. So when we take the push forward, we get R star composed with I star by the definition, like by the property of push forward, like we can split it, which is exactly like R composed I star. And on the right hand side, it is identity. So push forward of identity is the identity at the level of fundamental group. Okay. So we have R star composed I star equal to identity of a fundamental group of S1, which is Z. Okay. But fundamental group of S1 is Z. Fundamental group of D2 is trivial. So when you take 1 from Z, so I star of 1, so I star actually goes from Z to 0. So it should be 0. So I star of 1 is 0. But R star of 0 is 0 by definition of by the properties of homomorphism. And on the right hand side, you have identity. Identity of 1 is 1. So you have 0 is equal to 1, which is a trivial, like it is obvious contradiction. So it means it's a contradiction. So the assumption which we had earlier, like for all point in D2, like x in D2, f of x is not equal to x, it was wrong. So it means the contrapositive of that assumption should be true, which is there exists some point in D2 such that f of x is equal to x. So you can see like such a fancy statement one can prove with a little effort using the this strategies from fundamental group. So I finish here. Thank you for listening. Grazie, shukriya.
Thank you so much, Awais, for the talk. And now the floor is open to question. It seems to me that Shah want to ask some questions. So yeah, maybe we give him the opportunity to start.
Yes.
Shah, you can.
Also the video, Wajid.
Let me do
Make
that.
me visible, please.
Yeah, sure.
Mm.
Are you?
I want to see,
it, sir?
but I don't know how I can see.
Yeah,
Also,
what it will do.
because